Today I'm introducing you to parametric equations. Now, up until this point, most of your curves on the xy plane have been in the form y equals a function of x. Occasionally, you might have seen a function of x and y is equal to some other function of x and y, or conventionally we put that to be 0. And we looked at some of those in year 12 in the form of circles. And also we did implicit differentiation in year 13. We had situations that looked like that. But both of these types of equation are Cartesian. That is, they both contain just x and y, and there's just one equation. There's no parameter in these equations. Today we're looking at parametric equations, which is yet another way to describe a curve in the xy plane, except instead of having one equation in two unknowns, we're going to have two equations in three unknowns. So a typical parametric equation setup will look like this. So x is a function of t, and y is a different function of t, and t is what we call a parameter. Now that just means it doesn't have an axis, and when you come to sketch the curve, you'll have just the xy axes, and as you vary t, you will move around the xy plane, creating your curve. Typically, your parameter will be restricted to be between a couple of numerical values, or maybe it's just greater than a lower bound or less than an upper bound, or in the open case, you might have t could be any real number. But this typically will mean that then x will be restricted as well, not always, but typically, and also y. So we'll look at how we go about finding these bounds here based on the bounds there. Now, in the next video we're going to have a look at sketching such curves that look like this for different f and g. But today I'm just going to go from this parametric form, this parametric definition of a curve, to the Cartesian form. Okay, this is parametric. We're going to move to Cartesian form, and what that actually means is we're just going to eliminate t. So we get our x as a function of t, and we get our y as the other function of t, and we eliminate the parameter. So we eliminate t from this to give us a function, I'm going to call h, of x, y equals 0. It'll typically be an implicit definition, because if you could write it as y is some function, I've run out of letters now, let's call it y. If y is some function of x, then why would you not just start with that? Why would you have the implicit, the parametric form? So typically when you solve parametric equations to Cartesian form, you will end up with an implicit definition for the function, for the curve. T is usually used as the parameter, but not always. Sometimes theta is used, particularly when you're working with trigonometric functions. So just be a little bit flexible with what the parameter can take. Okay, so that's the crux of parametric equations. Let's have a look at three very basic examples in this video, and then next video we'll have a look at sketching them. So first, very basic example, we've got x equals t and y equals t squared, and we're told that t is any real number. So this is very basic because x is just the parameter. So if we want to find the Cartesian form of this, then we can take our definition of t and plug it into y. In other words, we're solving these equations simultaneously by eliminating t, and we end up with y is equal to t squared, but that is just x squared. Okay, now because t can be any real number, that means x can be any real number, and t can be any real number, which means y must be a non-negative number because you are squaring it. So y is greater than or equal to 0. Okay, and that's the values that x and y can take, which is just the parabola y equals x squared. Okay, not an interesting example there. Example number 2, a bit more interesting now. X equals 2 times the natural log of x plus 5, and y equals the square root of t plus 3. Sorry, that should be a t. That's a mistake on my part. And what we're going to do is we're going to find the Cartesian equation of this curve by eliminating t. So what I'm going to do is I'm going to take the definition here of x, and I'm going to say x on 2 is equal to the natural log of t plus 5. Raise both sides as a power of e, so that's t plus 5 equals the natural base exponential to the power x over 2. And then I'm going to subtract 2 from both sides to give me the definition of t plus 3. Now, I could have subtracted 5 from both sides to make t the subject and put that into here. However, I'm just looking ahead and I can see that I've got a t plus 3 in the square root. So why not make t plus 3 the subject? So I can just take this definition and put it straight in, rather than having t minus 5 plus 3. Yeah, I've got this. So I can then just substitute out the t plus 3 for this thing, and that's going to be y is going to be the square root of e to the x on 2 minus 2. Okay. And the bounds for your x and y, well, we can compare this to the definitions of x and y. So when t is negative 3, x is going to be 2 log 2. And as t increases, because it's bigger than or equal to that, the natural log function increases. You need to know that the natural log function is an increasing function everywhere. It doesn't decrease anywhere. And so therefore, it will carry on going up. There'll be no turning points. But also, you also need to know that as t tends to infinity, log of t will tend to infinity as well. So x can be any number bigger than or equal to 2 log 2 or log 4. Sorry, that's x. And y, again, we can compare the restriction on t with the definition in y. When t is negative 3, which is the lowest value it can be, y is 0. And then as I increase t, y is going to increase without limit. So again, y is going to be bigger than or equal to this lower bound of 0. Okay, that's the restrictions there. All right, and one final example before I set you with a question to think about. This one's a bit trickier. X equals cos of theta, y equals sine of theta, but theta is between 0 and 2 pi. So it's not as simple as just taking theta and making it equal to arc cos of x. In this case, theta is our parameter. Okay, that's not uncommon when dealing with trigonometric functions. Okay, instead of t. But the arc cos function will only take theta values between 0 and pi, whereas we want theta values between 0 and 2 pi. So that's not good enough. So the Cartesian equation is not y equals sine of arc cos of x, because that would only be a piece of the curve. You need to think about more of the curve than that. So for questions like this, it's worth thinking about some trigonometric identities. So recall from year 12 that sine squared of theta plus cos squared of theta is identical to the number 1. So we can take advantage of that for this definition. Now, sine squared is just going to be y squared. Cos squared is just going to be x squared. And that is going to equal the number 1 because that is cos squared plus sine squared. And we've eliminated theta by using the identity. Cos squared plus sine squared is 1. So this is actually just a circle. It's a circle, unit circle radius 1, centered on the origin. We can see that from the Cartesian equation there. The limits on x and y, well, theta takes the full range of the period between 0 and 2 pi, so therefore this is going to take its full range from minus 1 to 1. So minus 1 is less than or equal to x is less than or equal to 1, and the same is true for y, which makes sense. It is the unit circle centered on the origin. But if, for example, theta only went from 0 to 2 pi, 0 to pi, then that would be a semicircle, and y wouldn't go negative. It would be restricted between 0 and 1, because sine of theta between 0 and pi is between 0 and 1. Okay, so just bear that in mind. It's not quite as straightforward as thinking that's always between minus 1 and 1. Okay, so one to think about. This one is considerably trickier. and it's going to be the one that I first look at in the next video when we come to sketch curves. It is x equals 3t into 1 minus t and y equals 2t squared minus t cubed, and t is between -1 and 2 inclusive. This is not easy to eliminate t because it's a quadratic for x and a cubic for y, but it is possible to do. It's just incredibly messy. But if you want to have a go, and I'll reveal the answer at the beginning of the next video, and then we'll go ahead and look at sketching this one. Okay. Thank you very much for watching.